All right, welcome everyone to today's webinar titled Flexible Extraction of Today's Wide-Bandgap Devices with ICCAP GaN RF Solutions. Today I have my colleagues Abby Shih and Mark Knutson. There they are right now. They're going to introduce themselves in a minute. And I also have monitoring chat, Roberto Tinti and Malong. And if you have questions, enter them anytime in chat. And without further ado, Mark and Abby, welcome. You guys now have the floor.
Abby, why don't you go first if you want?
Okay.
Yeah, go ahead.
Hello, everyone. My name is Abby Shih, and I am the application engineer now in Europe. But I was in Taiwan and born in Taiwan, and I worked there for almost a year. Then I moved to Germany 2 years ago. So I'm in charge for the device modeling, technical, or all the software with the device modeling related application engineer in Europe, and it also include Africa and India and also Russian. So I will be talking about today mainly for this gallium nitride modeling on ICCAP. Oh, by the way, I've been working in Keysight for 10 years, so mainly in charge for the device modeling. So really happy to see you all today.
Thanks, Abby. My name's Mark Knutson. I've been in HP Agilent Keysight now 25 years. They can't get rid of me. And I've been focusing on device modeling, RF, microwave, circuit design, some system design, but my heart's in device modeling. So glad you guys are here today. We've got a lot of good things to share. So I'm going to go off my camera here, and I'm going to go to present here. All right. Hopefully you can see my desktop, right, Abby? Okay.
Yes.
All right. Okay, thank you. So yeah, thanks for coming today, guys. We know you guys are really busy. We're here to talk about flexible extraction of today's wide bandgap devices. And you might be sitting here thinking, you might have various reasons you came. And one of them might be applications are pushing you here, whether it's 5G, advanced radar, modern communication systems. LD MOS can only do so much, right? Because it's pretty good, pretty established, but there's new technologies that are pushing us to do more. So the only thing that's going down is the size of the devices, but otherwise it's higher power, higher frequency, higher efficiency. So we need a technology like GaN to go after that and be able to achieve those operational goals. Costs can be high, so maybe you're wondering about how I can drive down the costs, and that's what we're here to show you a sandbox that you can build on and a toolkit that you can build on that can help you drive down the costs. We're going to go into the device physics, or I should say Abby's going to go more in depth there, but I wanted to basically give you a heads up that what's so great about wide bandgap devices, especially heterojunction devices built on a GaN substrate. What's so great about that? One kind of teaser for you is that it can take a larger field, electric field, and a larger voltage, and then at a given operating power, you can have a lower current, which means smaller devices, which because of proportionality of area is a smaller amount of capacitance, and then you can get higher frequencies. But you have to navigate what we're going to look at today, some of the challenges like trapping, electrothermal, some of the different physics challenges. So thanks for coming today. I'm going to start off here and give you a little bit broader look at the sandbox we have. ICCAP is what we're going to use today. And then Abby's going to basically do a survey of some of the different models that we can do in our sandbox, and looks at the CMC models, ASM, HEMT, and MVSG. And we're going to look at she's going to look at some of the challenges. And I'm going to end with looking at some validating the model with large signal and load pull conditions in our circuit simulator, and then we'll leave some time for some questions. And as Carmina has said up front, if you have any questions, please feel free to put those in the chat, and we try to answer those as we go, and we'll leave some time at the end, and we'll definitely follow up. So I mentioned you got to have a flexible sandbox. What does that mean? You definitely need to have a turnkey extraction platform that has experience baked in. So we've worked with different modeling engineers and professors. You have to have the experience of the model baked in, but you also have to be flexible, be able to adapt. So I always like to start with a picture to kind of frame things up. Hope you guys like Star Wars. So this is a jogging trail out by my house, and for some reason in my city, they like to spray paint TIE Fighter looking symbols everywhere the gas line goes. So if you consider each of these TIE Fighters symbols a milestone in your device modeling project, you see that it kind of varies and moves around a lot. And from a project standpoint, staying on budget, achieving your goal of your device modeling project, you probably want that as straight as possible. And whether the path is curved, even more curvy, or it throws more challenges or more physics at you to navigate, you still want to basically stay on target. So that's my Star Wars analogy for you. Just like Luke Skywalker dropping the photon on the Death Star, we want to help you guys stay on target with a flexible sandbox. The only constant I think in device modeling is that there's more models coming, and the close corollary is more parameters to boot. When I talk to new device modeling engineers, I'm always just marvel at the fact that there's a thought that you can just throw 50 parameters in an optimizer and churn out the answer, and that's a good start, but not with the challenges of trapping and electrothermal and some of the things that we're going to look at today. You just can't do that anymore. You have to do more. So I do find that experienced device modeling engineers, I'll ask questions like what we're going to cover today, which I think most of you guys are, which is resolving challenges, how to navigate challenges, how to mitigate them. What's the right model for what I want to do, and how do I, you say flexible extraction, but can you show me that in action? What can I do there? The Keysight brings a lot of different tools to bear to go after all of these models listed here and more, and corner case modeling, reliability, aging, a lot of different technologies. The tool that we're going to show you today, ICCAP, it can handle all of these. Wanted to kind of put it in perspective for you. So we have a kind of an ecosystem of different products that are automated, discrete, or on wafer measurements, the extractions of the models, and then we also do model verification. ICCAP, which we're going to do today, if there's some of you out there that haven't used ICCAP, please feel free to reach out in the chat, and we'll follow up with more information. But I think a lot of you guys are very experienced with ICCAP, and you probably already know that it's a great tool designed for GaN and GaN RF that we're going to look at today. If you kind of break it into a pie, simulation, any simulator you're going to need out there, we can handle. In ICCAP, it'll simulate from ICCAP directly and take that model card, and circuit deck, and then measurement-wise, whether you're doing DC parametric, AC, S parameters, whether you're doing thermal control, wafer probing, or switch matrix. I would also add, we have one of the industry-leading ALFNA that can measure flicker noise and RTN noise, the lowest noise floor in the market. ICCAP can work with all of that kind of data and control that data. On the automation side, we have Python that is really powerful, 2.85 version today, and version 3 is coming out shortly. For Python, you can just literally go to any browser and get examples immediately. It's also built on PEL to do a lot of the scripting of the model, scripting of the GUI, and of course you can script how you look at the data. This is a list of a broader list, not necessarily all inclusive, of some of the different models that ICCAP can do, a wide breadth of models. The ones that we're going to highlight today, I guess I'll go ahead and use my pointer here, are the bold black ones. So we're going to compare EEHEMT, the Angelov GaN versus Dynafet, which we'll talk about a little bit more, and then the main stars today is what Abby's going to go more in depth on, which is the CMC physics-based standard models, ASM HEMT and which is a surface potential model, and the MVSG, which is a charge-based model. And we're not going to have time to cover it today, but certainly the similar flow can be used for power devices. And a PEMG is the instrument system that works with ICCAP. And you can look at silicon carbide and other kinds of power devices. So think field plates when Abby gets to that part of her talk. All right, so this is a quick run through on some of the history of GaN RF modeling. When it started, most people started using EE-HEMT and just the Angelov. They are empirical models, so kind of curve fit, polynomial curve fit models. Most people today, the workhorse is Angelov GaN. So Angelov did some extensions for GaN, but it's still an empirical model. So it's not going to cover things like trapping that Abby's going to look deeper into, and also electrothermal. It's just there's some extensions, but it's still just an empirical model. But it is a workhorse. And most people, customers we talk to today are still customizing the extensions. So Dynafet, we'll just talk briefly. It's not the main focus today, but it's a Keysight proprietary model. It's the most accurate model in the business in terms of low and medium power GaN devices. It's a neural network model, so you have to train it. So we have some data to show on that a little bit later. And then the stars today are the physics-based models, the Asm HEMT and the MVSG. And we're gonna go into much more detail why they have the stars. If we kind of compare, so we have three broad categories here: empirical, physics-based, and neural network. So Angelov GaN and EE-HEMT, they are scalable with some limitations. They do a really good fit on DC and small signal S parameters. But you notice when you go to a physics-based model like Asm HEMT and MVSG, you get a lot more fit under large signal conditions. It's fully scalable on geometry, on temperature, and it's a CMC standard. They literally started with like 10 models and weeded it down to these two over many years. So you can trust these two models. And then the Dynafet, I just wanted to make a comment that it's probably geared, in our experience, it's probably geared for low and medium power. It's the most accurate fit, small signal, large signal you're gonna get, but it has some trade-offs I'll show you in a second here. But it's a great model too. I wanna start with kind of the baked Alaska. This is a cooking show, just show you a few more parts of the data, and then I'll hand it over to Abby to go into the device physics. On the Asm HEMT side, these results, these next two slides are in care of Professor Chauhan of IIT. So the red is the measured data, and the blue is the model data from the Asm HEMT model using ICCAP. And so this is looking at power out, output power, and power out at efficiency over different real and imaginary load resistances. So really tight correlation there. And then if you bump it up, drive it up to a large signal and a harmonic balance situation using a tool like ADS, our circuit simulator, you can basically, the blue is the Asm HEMT model, and the symbols, the colors are the power out gain and power out at efficiency. It's really tight correlation as well. And you can see a dynamic load lines. This is sweeping over different time domain results, so it's a pretty robust model. It's not the star today, but I just wanted to end with showing how tight a fit for a low medium power GaN application. The Dynafet, which is a Keysight proprietary model, is amazing. Thanks to Dr. David Root and Dr. Jinjun Xu, who've done a lot of groundbreaking work with Dynafet. And you might be looking at this right here and think, what a big mess. What is that? That is, let's say that represents 50,000 measurements. So it's a dynamic load line that models more than just a static DC. But it's a neural network, so it could take a couple weeks, say, to train it. But once you do that, you can get IDVD fits that are amazing. These are zoomed in plots, just very tight, measured versus simulated. And the large signal, even up to the third harmonic, power out, very tight correlation. So that's all I have. I'm going to hand it over to Abby. Thanks, Abby.
So So good morning, good afternoon, everyone. This is Abby. And I think before we jump to this gallium nitride topic, I'm not talking about the dyno effect today because that would take another hours to cover. But today I'm going to cover a bit, more like the CMC standard model, which is both are the physical based model. And before I get started with into this topic, I would like to have a little recap of how the semiconductor physics was behind this. But before we start the semiconductor physics, let's start with the really basic Venn diagram, which I believe that all of you are very familiar with this Venn diagram. And in order to draw the Venn diagram, you have to find the reference plate, which is the vacuum level. And then you put your the work functions of the metals and the electron affinity of the semiconductor, and also the work functions of the insulator, and in the equilibrium state that you have to align your Fermi level. So in order to align your Fermi level, then you get your Venn diagrams. I think if you've learned semiconductor physics, that's probably the lessons that you have to learn after you graduate. You probably still remember how you draw this Venn diagram, because that would become more and more complicated if there would be a heterojunction and so on. And if you look at on the, these are the y-axis. So the Venn diagram from the metal, oxide, and semiconductor will be like this, and this will automatically form a service potential. But so if you look at the y-axis, which is the n-dope, p-dope, and n-type doping Venn diagrams, and you want to have your carrier to flow from the source side to drain side, and usually the carrier has to overcome the barrier that he found on the gate side under the Venn diagram. And in order to let your current flows, that you first apply a bias on the drain side, but it obviously does not really work. And then you have to apply some bias on the gate side, and then for somehow your current will start to flow. And this is really the basic concept of semiconductor. But this is also a very important concept that will be covered by most of all of the modeling physics and so on. So I was just saying that in order to increase the barrier from the metals to your semiconductor, you really have to increase the doping, and that will sacrifice the mobility. And that's something that the people don't want, because the high mobility that treasure the most for the 3.5 devices. So that's why it comes to the next concept, which is the wide-bandgap layer. But this is not the wide-bandgap layer we're talking about today. The wide-bandgap layer is the gallium nitride, but somehow the wide-bandgap layer concept is also in this MESFET, because you have to grow a wide band, and with a highly doping, you see this highly doping, the Fermi level is almost up, is even above the conduction band. And then so after you form you draw your band diagrams, then you will get a relatively high enough barrier to stop the leakage, and your Schottky barrier will be pushed a bit back to where the gate and the semiconductor is. And also by having this wide bandgap stuff, you don't even need to dope your semiconductor, which means that here is almost no doping, and you can have this mobility. You can take the benefits of the mobilities, and also you can have a high enough barrier which stop the leakage. And also you might notice that this service potential will form almost a quantum well. And inside this quantum well, if you calculate how this carrier concentration is, because it's far away from the intrinsic Fermi levels, then the carrier concentration increase quite a lot. So which means that the more of the intrinsic concentrations that you have for this material, the more carrier that you get. And it's almost like a 2D free electron gas. So which means that if you have the carrier that's inside these channels, then you will get a really free electron gas. It's like a freely moved gas. Sorry. Okay. So by replacing this concept to where we have we just, maybe I'll come back to the next slide. So these are the small bandgap. But if we replace this to the gallium nitride, and this is the topic for today, and for gallium nitride, there's two things that are quite special. One is the wordslide, the crystal structures that you have here, and it would automatically have a spontaneous polarizations, which if you form the aluminum gallium nitride and gallium nitride together, and you will get more this polarizations. That will increase a Shih charge on the surface. That will increase the surface charge on the Shih charge on the surface, and also because the lattice mismatch. If you grow things together and the lattice mismatch, and they will definitely also will have some because piezoelectric effect that will occur on the surface, and which means that by having this Shih charge on the surface, and now you could have including this a quantum well. Also electron gas, 2D electron gas on the surface, and also the Shih charge, then you get more and more of the carrier that can move on alongside this channel. So that's one of the really good feature that people benefits a lot if you're using the gallium nitride devices. And here's the really overview of how you compare the different materials with the gallium nitride. And obviously it's a wide bandgap stuff. And also since they're wide bandgap, so you will have a really high breakdown electron voltage. And so you might see the intrinsic carrier concentration is quite low, but don't worry because we just mentioned about the Shih charge. That would really generate quite a lot of the Shih charge on the surface. So you can also have many of the intrinsic concentration carrier, which I just mentioned in the previous slides, and which will contribute to the carrier in the channel as well. And also because it's kind of like a 3-5 devices, so it also has a really high mobility. Of course, it cannot compare to the gallium arsenide, but it's also relatively high enough. And like the saturation velocity, the more of the saturation velocity, the more currents that you got under the certain bias. That's for sure. And also the lower the permittivity, and you might get a smaller of the capacitance, and you might drive your devices to higher the cutoff frequency and so on. And also the thermal conductivity might be it looks not that optimal for this for this factor, but don't worry about this. If you grow this on certain of like the silicon carbide substrate, it will benefit quite a lot by this silicon carbide. It will dissipate the heat, so it can even drive up to a really high of the temperature. So which means that high voltage, high temperature, which means the high power. So that's why the gallium nitride is also very popular nowadays on the power devices application. So this is a really just a comparisons of the graph, and you will get the slides. So I will not go through these details for this graph, but you'll get the presentations after this meeting. So that was about how this gallium nitride was so popular nowadays. So let's talk about the models that we have in ICCAP. So for the models we have for ICCAP, before we talk about the model, I believe that many of you are the experienced or the senior user, or even they've used ICCAP for quite a long time, probably even longer than I have because I've been working here for almost 11 years. So, but I think you might be very familiar with this modeling, and they are modeling like the charge base, the service potential base, like the BSync IMG CMG are the service potential base, and CMG6 is the I think that's a charge base, and the one that you probably also very familiar, the BSync 3 and 4, they are the threshold voltage base and so on. So there are many of the ways to describe the same devices, but they have a different ways to describe the same devices, and the main goal is also to find the way to describe how the carrier behave inside the channels or inside the tunnel. And so the goal is just to find the equation that can describe below or above or the subspecial areas of the currents. So the first one I'm going to talk about today is the virtual source. It's also the MIT virtual source modeling. And this modeling is quite simple, and it has really not that many of the parameters. And the concept is also very simple. It would just assume that the current is equals to the equals to the charge times the velocity. This is just physics, right? The charge times the velocity, and this velocity is the bias dependence, which was also mentioned in the first 2 slides. The more of the VD that you apply, the more of the charge that you will get. And so in general, to describe a carrier, the currents in the channel, this is quite simple equations that you can get. And if you still remember the semiconductor physics in your university, and these are usually how you describe the linear region and the saturation region. And here I just try to simplify stuff because the saturation region, we assume that it's saturated, but it does not really saturate because of the dipole or because the short channel effect and so on. So, but let's just assume that's a really simple case. And this virtual source theory was just to want to find how you can connect the linear region and saturation regions to connect these two regions together to make it one equations, right? So so you might see in the linear regions, then the velocity, if you compare to this the equations, and the linear region, the velocity is the form like this, and also in the saturations like this. So how to find the correlations between this one? So they come up a concept of the transmission equations, and this one you can see that obviously the slowest one that would dominate the whole equations. Then that's how this equation comes from. And if you just do some just take these transmission functions into your equations, and then you pretty much get the concept of what is the virtual source equations is from. And these are virtual source, and usually it happens on the maximum band gap of the band diagram here. And also the velocity is, we assume that it's just on the top of the velocity that's on the top of, it also appears on the virtual source positions. And so these are the virtual source equations. And the next one is the numerical one, which you solve the surface potential. And that's also probably the one that I am more familiar with, because that's how we calculate at school, and you use the concept of divergence of the displacement is equals to the Shih charge, and also the electric field is equal to the delta of the phi, or the static potential, and also the delta square phi. Then you put these two equations together, and the delta square phi is equals to the Shih charge over the electric constants, and so on. So which means that once you find the carrier, the charge behavior in the Venn diagrams, and you solve the surface potentials, then you will pretty much get your currents here. And so this is the concept of the surface potential. They try to solve how is the Fermi levels or the quasi-Fermi level will vary inside the channels, and then they calculate the probability of the concentration carrier will appear on the energy levels, and they put it all together to calculate how the currents flows inside the channel. So this is the concept. They really solve the Poisson-Boltzmann equations. And the first one I mentioned, the MIT virtual source is, the MIT virtual source is the one of the model CMC recognized, the MVSG. So the one is MVSG, means that MIT virtual source, and G represent the gallium nitride. So it's actually the MIT virtual source gallium nitride model. And if you still remember the slides, and so this equation might be very familiar to you. And so these are the charge that it's on they describe the charge on the source and the drain side. And also they have the saturation velocity, and they also have the transmission function. And this transmission function has the beta form. It's part of the model extractions that you can use this beta form to adjust or to smooth, to find a better match for the transition from the linear to the saturation regions. So these are the beta form. And actually these equations also include the trapping and the thermal, and all this equation will be inside these equations. And if you wanted to know more about this equation, here's the paper for you to refer. But in general that it does, for example, the charge on the source side and the charge on the gate side are totally relevant to the bias on the gate and the bias on the source and bias on the gate and the bias on the drain and so on and so forth. And also the thermal, these are the thermal terms. And these are the terms which to switch from the sweet conversions to the strong conversion side of the threshold and so on and so forth. And the next one is the Asm model. Just like I mentioned, that the Asm model is just to solve the Poisson-Boltzmann equations. And you might see that the equation is quite simple, which related to the surface potential from the source and the drain, and the ds represent the difference from the source and the drain. And you don't see the you probably will see that in this equation, it has only one equations, but it actually cover from the before the threshold and the subthreshold and after the threshold voltage. So this equation pretty much cover all of the regions of the bias. And the reason for this, why it covers so much, because it actually divided actually it calculates the Fermi levels below or in the subthreshold regions or above the subthreshold region and so on. So it put all these equations into just by solving the Poisson equations, by solving the surface potential equations and put it in the unified form. So that's why it looks like this. And also it also has the trapping mechanism and self-heating mechanism including all in these equations. So it looks quite simple, but if you look into the paper like this one, it will teach you how to solve this Poisson equations and so on, and how they calculate the drain side and source side. And this is actually the VG is equals to the VT minus VG minus the V thresholds and so on. So this really looks like a really simple equation, but it actually has really of the mechanisms behind this. So this is the surface potentials equation. And so in general, these two models cover all of this stuff, like the short channel effect or the self-heating and velocity saturations. You might also refer to all this paper I mentioned in the slides. They have all this calculation included. And if you are using like the power device, which is not the cover of this today's topic, but if you have this the power devices, then you will maybe consider of the field play. And these two models also talk about how you put this field plays models inside the equation and so on. And so what makes the gallium nitride like a special model? So it actually has some challenge that you have to face. So these are the challenge, like if you have the field play, how are you going to describe how the field play will affect your models? And if you have a self-heating, and how you're going to put it inside your equations, and also if you have a trapping, how you put it inside your trapping and so on. So in the next sections, I'm going to talk about why that is a challenge for the model engineer. So let's first talk about the trapping. So what is trapping? So the trapping means that if you use the pulse IV and you first define the quiescent point, the quiescent point means that for the VD, that if the VD quiescent point is 3 and the VG quiescent point is minus 0.2, which means that every time you bias your devices to certain bias and come back to 3, and so as to the gate bias, and then you got the maybe IV curve like this. But if you have changed your quiescent point to another point, and you find that the IV curve does not really look like what you got before, so it's called a new workout. But then the question is which IV curves to use. It seems like the model couldn't the device couldn't repeat itself. So if you're using this quiescent measurements. And that is a lot of research behind this. Like there's actually the gate lag, there's actually a drain lag, and the gate lag is if you just put this VD bias to 0, which actually got no current flows, and you just keep the quiescent point of your VG on and off, like the 0 and -8, and then you will get this phenomena. That is probably mostly contributed by the surface trap. And there's a drain lag, and drain lag means that you put your gates completely off, and then you drive your drain size to a certain of the positive voltage and let the current let the channels on, and then you'll get another of the IV curve. And this is actually contributed not only for the service defect, but also from the buffer. And so these are so forth. And these are the paper from the ASM model that shows that how accurate the model was able to capture this trapping based on the different pathways and the different quiescent point, and how this will also affect their dynamic on resistance. And this how this ASM and MVSG model will put this trapping mechanism into their models and get the pretty much correlations between the simulation and measurements fact. And why that's important, because if you're designing the PA, then you will expect that your currents will goes up if your power input goes up, but actually collapse. So that's why we call it current collapsed. Okay, so this current collapse, like I just mentioned, it caused from the gate lag, it caused from the drain lag, and that will because of the service trap and the buffer trap. And these are something you cannot avoid if you are using these gallium nitride devices. And so in order to better capture this, put this physics mechanism into the equation, it's become somehow a challenge for a model engineer nowadays to get a really good models. So these are another paper shows that if you have the drain lag, if you have the gate lag, if it depends on where you bias your devices, and you get a different IV the power input to IV curve. And the next one is self-heating. So the self-heating is quite obvious, and I think it shows also in the gallium nitride devices. And it means that if you constantly bias your devices, then the carriers start to heat up, and the compensations of the heats up, you will see that your current start to clamp. So it's quite obvious in the conducted graph that it shows two of the slope. One is that you see that the transconduction becomes to slow down, and then it goes really further, and that was where the self-heating occurs. And this is actually where you can also find it quite obviously when you're doing the modeling. And if you goes up to the higher bias, then you will get more and more of this two slope stuff while you're doing your extractions. And that's where you have to turn on the RTH, which is also one of the parameter that they put it into the models, that you have to switch this equations on in order to put this feedback of the resistance and the capacitor thermal into your core model in order to capture those mechanisms. And actually there is some way to exclude this if you're using the pulse measurements. And then if you're using the pulse measurements, then you will get the resistant thermals to 0. But you really have to pulse in the right pulse, otherwise you'll get the trapping again. So it's also quite a state-of-the-art stuff that how you can design your measurements way in order to get the right data and for you to extract the right parameter and so on. So this is also another challenge for self-heating, not too small or not too long pathways in order to capture this. And the next one is the field play. It's not the focus, like I said today. It's not the focus today, but this is also included in these two models that they have if you're using this power devices, then you have the field play, and the field play is the purpose of having the field play is just to reduce the breakdown, or just extend the breakdown voltage, or larger the breakdown voltage. The more of the field play you have, then you will you will minimize the peak of the electric field in the channels, and so on. And there are several research as well that how this the field plays will affect the breakdown voltage, and for so on. Like the more of the field play, then the more the breakdown voltage they will get. But more of the longer of the field play, of course, that you will also get a longer the larger breakdown voltage. But in composition of you might get a small of the MX and MXM, the cutoff frequency will be sacrificed and so on. So it's also a really a challenge for the design engineer or for the fabrication engineer to find the field play. And these models actually cover how the different field play, that the gate side, the gate field play on the drain side and the source side, and the source field play on the gate side, and so on, how this will affect the CV behavior, and how will these equations describe the different field play will have a different of the curve, and so on and so forth. So this is also another challenge for the power device especially. Okay, and the next one is the RF devices. And for the RF devices, and of course that you have your equivalent circuit. And for this equivalent circuit, actually, in these two of the models, they both have some suggestion for how to extract this the RF components inside your equivalent circuit. And also, I will show you in ICCAP that how this equivalent circuit was also taken into account in ICCAP extraction. So to be brief, because the next one I'm going to jump to the ICCAP. So before, just to summarize that, either the MVSG or the ASM model, they are both using, one is the charge-based, and which the virtual source, and the other the service potential. In either way, they all prove that either the trapping thermal or the field play, they put some equations just to modify how these of the characteristic will be really good matched in their equations. So in ICCAP 2018, we started to have this the two of these models. So because of the time, so I would just open up my ICCAP instead of going through the slides, and the slides will be left to you if you download this. Just read it. So I'm just simply going to the ICCAP. So this is ICCAP. For most of you, might or might not familiar with us, it's okay because it's ICCAP and it's 2021 update 1. So your ICCAP might look a bit different like mine because I'm using the latest one, which is not released. And so the reason I'm going to demo this is because ICCAP 2021 update 1 start to have the Python 3.8.5. I'm going to show you this later as well. But in order to open this models, that you go to the examples here and open the model file, and there is a hemmed model, and inside the hemmed model you will see this GaN CMC, and in the GaN CMC there is a ASM hemmed model and MVSG. So either of those, there is a model ASM modeling, and just open this one up and double click, and it comes along with the gallium nitride utility. And this model you're going to use a lot from this utility, and we're going to talk about that later. And the same concept is for the MVSG. So either you click on the ASM or MVSG, it will give you a window like this. So I first introduce, this is the dark mode of ICCAP. And so in ICCAP, if you're familiar with ICCAP, it still looks like ICCAP does not have any difference, right? So first of all, we look at this circuit. So the circuit is using the ADS, using ADS simulator. So, but if you're using the HSPICE or Spectre, I think they also support the ASM and MVSG models. But you can also use ICCAP to activate that. But I'm going to talk about the ADS today. So these are actually the ADS models. And if you go from the top to the bottom here, and this is actually what you have to do for the modeling. And first of all, you load the device modeling. You load the measurement data, but it's not necessary to use the load device data. You can even load it one by one by using this. Just click on this. Just click on import your data, and you can also import your data, but you have to follow certain of the rule, but it's not the focus for today. And also to name the devices, then you can also change the devices, the name of your devices today. And also you change your work directory, and these are the work directory, which I have pointed to the workshop today. And this is very important, that it gives you the windows of how the physical process information that you have you have to put before you start the modeling. For example, the length or the width or the access regions for the gate to the drain, or the access regions to the gate, from the gate to the source, and so on, blah, blah. There's a lot of things here you have to enter before you start your modeling. And after this, after you put everything here, and there is the extraction flows. So maybe I'll come back to the slides for this one. So you can see that inside the core model, they have some LG outside of this. And this is actually contributed from the path capacitors or the metallized inductors. And these are something you have to put it into your modeling as well. So this is what this part was about. You put this resistance here, and after the resistance is extracted, and these values will be put it here, right here. Yeah, so you follow this up, including the L and C, L and R stuff here. Like then you'll be able to put all this sub-circuit outside your core. And so actually this sub-circuit, if you put it in the ADS, it looks like this one. So these are actually the sub-circuit that you have to put outside your core models and so on. So this is actually the first part. So after you've done the first part, and let's go on to the second part. And the second part is for the extractions. So this is the extractions interface. And this extraction interface, well, you see, so if you want to do the optimize, so this is the extraction interface. That looks a bit not like ICCAP right now. If you want to add more of the parameters here, and you just click on add, and you can put your stuff here. Like if you want to have the UT here, then you can put UT here. If you don't want to do this, you can just unselect this. Or if you just want to see some of the graph here, and you can just click some of the graph here. And if you want to do the optimize, I would suggest you switch off all the optimize and click on the first one and hover up and choose the place that you want to do the optimize and click on optimized. And actually the ADS will start to do the optimize for you. You can see this optimized, and every actions will be memorized by the actions, which means that if you don't like this, if your extraction is finished, let's just click on this one. Okay, so you can see the extraction is finished, and if you don't like this, you just click on 0, and it will come back to the last step that you just moved. But if you like this, just keep on this one, and you will do more of your stuff here. And if you want to do some tuner by your hands, then you just use the tune bars here, and you can see that things were just moved here. And well, like I say, if you don't like this, click on OK, and you see, well, I like that last one. Just go back to the next one. Yeah. And well, this is only this is the concept of how you use this tool. And also, if you want to add some graph here, you can also add some graph here. And if you just put on some, I don't know, just put whatever the graph here, and you will be put it here right away here. And if you don't like this, just unselect this. Okay. And so this is the pretty the concept of how you use the tool. And let me just introduce you another good feature which I like a lot. It's the Python. So if you use, because ICCAP now supports Python, so you can even use your you can even open your, just use your data. And some of you might want to see how this graph will just change on the 3D perspective, right? So if you just, I don't know, if you just change this stuff, I don't know, see that in the 3D graph, it will just interactively moved based on the parameters that you just changed. And this will give you more ideas of how it looks like on the 3D graph, right? But this is maybe not the one that you will want to do for DC, but for some power user, they might want to, like, they want to see how the CV was changed depending on different bias, right? So these are the concepts for DC, and if you go to the CV, it's also the same. And for this CV, it's also, I won't repeat that again. So let's just come to this S parameters here. And for the S parameter, you see that there's this SCG, SCD, and so on. So it's actually using this graph. And how they calculate this was by using the utility So if you look at this one, and it's calling the utility here is called schematic, and this schematic is actually calling the utilities here. And inside this utility, and well, inside this utility, sorry, is actually using this one is actually using the calculations here. And what is calculate? I also put one slide here, so you may just refer to that. So how this was calculated is based on this S parameter. Then if it's in series, and you can just sum up, and if you know your RD and RD and LD, and then you subtract this, and you get your core devices. And once you get your core, and you can calculate how the CGD, CDS it's about, blah, 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 and so on. So these are the concept of how this toolkit was working. So, but you don't have to worry about this, and you just click on this, the demos here, and then come back to the CV, and here's the CGS, CGD, and so on, blah, blah. And well, so you might want to know how this 3D will look like if it's moved on a 3D graph, right? So it's the same, just put your data inside and try to activate it, any of the simulators here. And the simulator will give you, so this is the same like the DC part, but if you're using S parameters here. So if I open up here, so it's a CDS versus CDS. Okay, so if you also wanted to tune your stuff here, let's just tune your stuff here. Okay, let's see how the 3D graph is. Okay, so I know that many of the engineer wanted to know that how this CGD, CDS, CGS was versus two different bias, and you can also check on how this would change depending on different of the parameters that would change the graph, and so on and so forth. So actually, this just tells you that how flexible the toolkit is about how you just adjust the different parameter, that you can either check it on a 2D graph or the 3D graph, or you can even add some of your programs inside. It's totally open environments for you. And so I think for the modeling engineer, that all you need is the flexibility of the tool. And then after you've done these extractions, and you can just save your, you can just save your devices here. You can just the save modeling state, and you can just save the state, which is the MPS format, and the model parameter set. And after saving this, and you are free to go to put it in the ADS. So I would just hand the floor again to Mark.
Thank you, Abby. I appreciate you showing the new Python look at the same time. That's great. All right, let me try to take the ball back here. Thank you. All right, so as Abby said, if you guys can all see this, as Abby said, you can go into ADS and basically import that MPS, that model. Like if you did the ASM HEMT and the MVSG has a similar extraction flow in IceCap, and you just bring the MPS file, the model file into ADS through tools in ICCAP import. And that's going to bring in the intrinsic model. Anything parasitic that you want to put around it for your application, you have to do that. So we're going to look at two things, load pull, and then we're going to look at it in large signal conditions to kind of validate the model. We're going to use ADS, but as Abby said, there's other tools that you could use. I'm partial to ADS for several reasons. On the load pull side, I like to use ADS because one, you can import measure data very easily from like Maori or Focus Microwave, something like that. Number two, you can easily draw the contours, and I'll show you that. Number three, you can find the optimal load. You can put in different types of reflection coefficients. It could be a circle, a rectangular region, a pi region at the harmonics, and find the optimal load. And fourth, two more reasons. Fourth being you could basically do advanced topics. You could do a wideband input and see what the impact is on like the EVM through a load pulled device, like a power amplifier. And the last but not least, There's ways in ADS to set up the optimization of a load pull device to basically make sure it converges under like, extreme conditions. If you want to know more about load pull, these are some great YouTube videos. Andy Howard, Anurag Bhargava are some of my colleagues that have done some excellent work there. I encourage you to check those out. And this is what it would look like in ADS, and I'll show it to you with the last minute I got here. I'll show it to you in ADS, but you basically use an S1P equation. You can build like a load based upon the harmonics, and I'll show you that. You can set the harmonics at the different, the load, the source at the different second harmonic, third harmonic, fourth harmonic. You could build an active load. And then this is again in care of Dr. Chauhan at IIT, but this is at one power level, the tight correlation you get on power out, power added efficiency of an ASM model. You can also test it, and I'll show this to you in ADS. So in ADS, this is what it looks like. And you can basically define, use the S1P equation. You can define load conditions under this impedance case. If you didn't want to build this yourself, it's super easy in ADS. You go to design guide, load pull, and I would look under things like the constant available source power and swept power. And you can even get special templates like EVM contours, ACP contours at a certain X dB compression. So check that out under the design guide. And just wanted to show that. One last thing, and we'll wrap it up, is on the, let's see right here. So you can also use the ASM model under like a condition of different frequencies. You present a different load at different frequencies, and the simulation you can get a very accurate picture under an accurate load conditions, what the device sees that you extracted in ICCAP, the gain, the power out, and the power added efficiency. So that's a really quick run through, but that's how you're going to basically validate the model. So just wanted to recap. We've got a tool we've worked with device modeling professors and experts and come up with an extraction flow that you can build on and get quickly started. The model intelligence is kind of built into the flow, and there's flexibility built in, so that's going to increase your efficiency. GaN is going to become bigger. It's supposed to be multi-billion-dollar business in 2025. So I want you to ride that wave, and it can be challenging. Some of those challenges with trapping and de-embedding and thermal issues, but fortunately we're here to help. So let us know how we can work together and help you guys with first pass success. And this is just a final run through of the products that Abby demonstrated today up on the top left over here. If you have any of the other models, they are also available for GaN and ICCAP. There's some great case studies like from Dr. Chauhan and IIT, some other application notes I would refer you to. And if you want to dig more into ADS, you can take a look at that and how to validate the model. And just hope you'll get out and try it and let us know how we can help. So please contact us. Thank you so much for your time today.
There was a question for you, Mark, from Jerome that he asked, what set of measurement is required to extract the ASM model and ICCAP? And that question was in chat.
Yeah.
Go ahead, Abby, if you want.
Yeah, this is a really good question. So I think it definitely includes, well, for anyone who doesn't really have time for that, I'm sorry for a bit delay. So first, the DC and of course, you have to have the DC and the CV and S parameter, and also for the trapping, you need to have a different quiescent point. It really depends on your application and so on. So, but it's I would say that's not really easy to tell you that what kind of the measurements that you need to get. But DC and CV S parameter and the different bias of the S parameter, and also the different quiescent point of the device is definitely necessary. And for some, if you want to have some temperature dependent, of course you have to change the temperature. And these two models also include the thermal parameters and so on. Well,
Yeah,
basically the MDL, which I just shows, the file I just shows, you pretty much have to fill in each of this setup. So just go through all extraction, but it's not actually fair. It's not really enough. So it really depends on your devices. And so that's why I say it depends on your devices and as much as you could, and we can talk about that offline.
Yeah,
good question.
we had a lot of questions about licenses and current, and Roberto, I'm thinking this might be a good question for you. So folks, we're asking for trial licenses. I know that we can provide them, no problem. Just ask us if you'd like a trial license for ICCAP. Folks asked, are these features in ICCAP 2020? You know, Abby showed a newer version. And also, do you need licenses to use the ASM example in utilities? So Roberto, do you want to handle all of those?
Yes, hi everyone. So as far as the licensing concerns, yes, the package shipped with ICCAP 2020, so it is available. It does require license. There's actually two different licenses. One is a bundle that includes ICCAP and the GaN extraction, but also you can purchase this as a separate add-on. So there's those two ways. As far as some of the capabilities that Abby has shown today, specifically the 3D plots, those requires a Python 3, and so those will be available actually very shortly. And we are releasing 2021 update 1 in about 3 or 4 weeks. And so that would be the first ICCAP release that supports Python 3 and allows building those kind of plots. So I would that was a little bit of a preview of something that is coming up.
All right,
right.
thanks everyone. I'm going to go ahead and stop the recording.